Hi everybody, thank you for taking part here today for our online Space Week seminar, especially our invited speakers, but also to all the students and educators. There's a lot here. It's very nice to see such a strong interest in exploring our understanding of the universe. This is our third CosmoVerse seminar, exploring our shared cosmic history with students and educators from across Europe and neighboring areas. CosmoVerse, as you may have seen, is a network of over 600 researchers in Europe and over 800 globally, with the aim of unifying efforts and confronting the most pressing questions in our understanding of the cosmos. So the main aim of CosmoVerse is to establish a synergy between theoretical data analysis and observational physicists working on frontier challenges to understanding how our universe is expanding, evolving, and the source of these processes. To know, you can also follow us on Facebook and Twitter or X, as well as on our website. And let's shift now to the next presentation, to our second speaker, who is Dr. Dani Leonard, who is a lecturer in data science at Newcastle University. Their research applies statistical methods to analyze large data sets from cosmological galaxy surveys. They use Bayesian parameter inference and model comparison, as well as machine learning techniques to constrain and compare cosmological models. They are a full member and builder of the Rubin Observatory's Legacy Survey of Space and Time Dark Energy Science Collaboration. Dani, please start in your own time.
Okay. So thank you very much for everyone for being here, and thank you, Manos, for giving a great first talk. So as Jackson said, I'm Dani, and I'm going to pick up basically where Manos has left off. And I'm going to continue basically with what we can learn about the large-scale properties of the universe from observing the stuff that's in it. So the galaxies and stars and the light from the distant past that Manos has started to talk about. And finish up by talking about some of the work that's being done in these modern observational astrophysics facilities that Manos introduced at the end. And that can hopefully tell us something about these sort of intriguing sort of tensions and cracks in our understanding of our standard cosmological model that CosmoVerse is focused on. So obviously Manos has given a great introduction to this, but I'll just, I guess, recap a little bit, which is that to tell you what is cosmology. So cosmology, as we've seen, is the study of the history, the composition, and the physical laws of the universe. So that's what we're really interested in learning. And I think this is a diagram that packs in a lot of the information that we know and what we think we understand about this. So going from, on the left-hand side, the very, very early universe with this Big Bang that Manos introduced, through early time, where we see what was labeled here as an afterglow light pattern. That's the light from the cosmic microwave background that was just talked about as well, going all the way to the right-hand side of this diagram, where we see the development of structure, galaxies, planets. And I'll come back to this diagram in a few minutes to illustrate some of the things I'm going to talk about. So one thing that's kind of interesting here, though, is that we can see that the light that Manos mentioned from the very early universe on the cosmic microwave background, we can see that on the very left-hand side, the structures that we can kind of see beginning to be illustrated within this light are actually the seeds of what's going to allow us to create the structure that we see in the later universe. And in reality, these structures of galaxies and stars that we see in the later universe are just the tip of the iceberg in terms of everything that's there. So that's the first thing I kind of want to talk about. How there's actually a lot more in our universe than what we see with visible light. So I've labeled this slide badly behaved galaxies, and we'll see why in a second. So We have on the left-hand side here a photo of Vera Rubin, who was a scientist, an astronomer working in the 1970s and 1980s. And she and others working with her were making measurements of the rotational velocity of galaxies. So what this means is that they were measuring the speed at which the matter in the galaxies was rotating around the center of the galaxy. So as a function of the distance from the center of the galaxy. So we have a plot here that kind of shows what we mean. We're measuring the velocity at which the matter is moving around the center of the galaxy as a function of the distance from the center, which is on the x-axis. So the thing that's really interesting about this is that if we have an understanding of the mass distribution within a galaxy, so if we think we know what stuff is in the galaxy, we could calculate what we would think this would look like. And this is because the way that the matter rotates around the center of the galaxy is really a function of gravity. So we could do this using general relativity, as Manos introduced, but actually you can do this in a really simple way using just Newton's laws of gravity, which I'm sure some of you will have seen already in your classes potentially. But just using the basics of what we know about gravity, you can work out what you would think these rotation curves would look like. And what we see here is that the measurements that Vera Rubin and collaborators took showed that the velocities, so the speeds at which the things are rotating, the stars and the gas are rotating about the center of the galaxy, are actually much higher, much further out from the center of the galaxy than could be explained from the mass in the galaxy that we can see. So if only what was in the galaxy was what we could see in terms of stars and gas, what we could observe, we would have the curve with the dashed line that says expected from visible disks. So the visible matter would predict that we would get that. But what we actually see from observations is the points with the yellow and the blue points with the error bars, which, as you can see, are much higher, much further away, so much at higher R values, further out on the graph than what we expect. And what this started to be really strong, convincing evidence of when we see more and more of these types of observations is that there must be something else there. So this is what led us to the introduction of this component of the universe that is now part of our standard cosmological model called dark matter. So it's a type of matter that we can't detect electromagnetically. And our modern measurements of this type and also of other types that we have since been able to use to pick up on this signal of matter that's not there, that we don't see, suggests that it makes up more than about 80% of all the matter in the universe today. So something very important that we're not actually seeing directly, but that's taking up a lot of our matter energy budget in the universe. So what does this tell us about the universe? Well, so it changes the way we think about formation of structure. So that structure that we saw in the image forming later in the universe. So if we think about a galaxy without dark matter, on the left-hand side here, we have an artist's illustration, and it would just be the central part with the spiral arms. So if we didn't have dark matter, it would just be the central thing that we kind of might think about when we think about like the Milky Way galaxy or something similar to that. But what dark matter tells us is that we would actually expect this galaxy to sit within a larger structure called a halo. So this is the blue in the picture on the left here. And this is where all the extra mass that sort of meant that rotation curve was higher than we expected would be sitting. And on the right, we have what's a visualization from a big cosmological computer simulation. So simulating the development of structure in the universe as a result of this dark matter. And we see that it creates this web structure. So we have bright, high density nodes, which are interconnected with these filaments. And galaxies we would actually expect to form in the very brightest parts of this map. But what we wouldn't necessarily see without the dark matter or with different kinds of dark matter is the density of these structures connecting all of the different nodes and creating this web. So we think that by observing these galaxies, because the galaxies form in the higher regions of dark matter, we can also trace indirectly the dark matter in the cosmic web. Okay, so that's dark matter. The other thing I want to talk about is another component of the universe that has a similar name, which we'll get to in just a second. But to introduce it, I want to come back to this picture. So you can see that in this, if we take this as being time from left to right, like I said before, we can see that the kind of the cone of that's illustrating the universe is getting bigger as we go from left to right. It's gradually getting bigger. And that is to do with the expansion of the universe that Manos introduced. So the universe space is expanding. But as we get closer to today on the far right-hand side, we see that actually there's a bit of a flaring out. So it's not just getting bigger, but it's getting bigger faster. So the expansion of the universe is speeding up. So what's going on with that? General relativity, which Manos introduced as our theory of gravity, tells us that if we have mass and energy in the universe that is made up of the kind of normal stuff that we think we have, so regular matter, even dark matter, light, like photons, normal radiation, gas, anything we can come up with that's like usual stuff, is going to mean that the effect on like the space-time of the universe that Manos was talking about is that the universe might be expanding, but the rate of that expansion would be slowing down over time. So we kind of thought this should be the case, that if anything, the rate of the expansion should be slowing down, because that's what would happen as a result of having like normal stuff in the universe. And we thought this was true so much that we defined something called the deceleration parameters. So is the expansion speeding up or slowing down? Well, we think it's decelerating rather than accelerating. This is kind of in the 90s. So we said, we kind of try to measure this. We're going to define a parameter to measure. We're going to call it the deceleration parameter because we're so sure that the expansion is actually slowing down. Okay, but as we can see from this slide, no, it's not slowing down. So what we see here is some measurements from the late 90s, where we found definitively for the first time something very different. And what we're looking at here is basically kind of a grown-up version of the measurement that Hubble did, that Manos introduced. So the diagram where we saw the velocities on of galaxies getting higher as we went further away, this is like the next step of that kind of measurement. So when Hubble made that measurement, he could only measure galaxies very close to us. And that was just because of the technology available at the time. And this is part of what we're talking about with like the technology really pushing discovery in astrophysics. If we look at measurements of much further away galaxies, like we were able to start doing at this time in the late 90s, we can use the fact that their light actually takes time to get to us to trace what is happening in the universe at earlier times. And what we see here is a measurement from one of the two sort of main papers that showed that the rate of the expansion was not slowing down. Because if it was slowing down, we would see the distance as a function of velocity here looking like the green line. The black points are our measurements. And so what we see is that it actually much better fits the case where this expansion is speeding up, so accelerating now, but was previously slowing down. So what could possibly be causing this? And so this is this component of the universe that has a similar name to the one we introduced before, but instead of being dark matter, it's called dark energy. So when we look at the equations of general relativity, we see that the one thing that could actually one of the things that could actually cause this accelerated expansion is if the universe was dominated by a novel type of energy that has weird properties unlike anything we've seen. So the main thing here is that you'd have a negative relationship between the density and the pressure of this kind of energy, which is super weird, right? You wouldn't expect that like a higher density would cause a negative pressure, but that's what would actually work to give us what we see here. And this is what we've incorporated in terms of our cosmological model. One way to think about this is that the dark energy is actually an energy associated with the vacuum of space itself. And so the simplest description of this dark energy is what we have accepted as part of our standard cosmological model, since these measurements in the late 90s that actually won the Nobel Prize several years later. But we don't actually physically, like on a particle, like microphysical level, know what either this dark energy or this dark matter is, even though it explains our observations incredibly well. And so in the last couple of minutes, I want to talk about the sort of influx of data that we have at the moment that is coming to try and explain and understand some of these theoretical confusions that we can already see just from the fact that we have like 95% of the matter and energy in our standard cosmological model is stuff we don't understand on a microphysical level. So I go to the next slide. So we're kind of entering the era, and we have been entering the era of precision cosmology. So we have all of this data. I think I'm not going to have time to talk about all of the different kinds, so I'm going to have to flash through things a little bit quickly. This is an update on the measurements from Penzias and Wilson that Manos mentioned of the cosmic microwave background. So it turns out that you can not just measure the temperature of those photons across the sky from the very early universe, you can measure little tiny variations in different parts of the sky from what we see from this. And this actually is indications, like I said at the beginning, of fluctuations in the structure in the very early universe that lead us to develop this cosmic web. And so we have this very precise measurement of this from the Planck satellite from the last 10 years or so. And we see that we can measure summary statistics of this that fit our standard cosmological model very well. Another way that we have of measuring things about our cosmology is through this really interesting effect called gravitational lensing. So it's kind of like lensing in the sense of like your glasses lens the light that comes through them. But instead of it being optical lensing like that, it's a case where actually you have light from a background source of light. Here it could be a galaxy. You have mass in between the observer, me, and that source, the galaxy far away. And the light from that background galaxy is actually, its path is changed as a result of the intervening mass. And so the path is distorted, it's lensed in the same sense as it would be in a pair of glasses. And this is actually a result of general relativity. So same as what Manos was saying about the space-time being bent and distorted by the presence of mass, you can imagine that doesn't just cause like the behavior of massive objects being attracted to each other to change. It can also cause the path of light to change, and that's what gravitational lensing is. And the cool thing about that is that gravitational lensing doesn't care if that mass is something you can see or not. So gravitational lensing is affected by dark matter. So that's a really cool way that we can probe and understand the dark matter distribution. And there's a map of this from the Dark Energy Survey on the bottom left-hand slide here. Sorry, I'm having a lot of trouble with my slides. Okay, I will just wrap up by showing some amazing images from two surveys that are going to be giving us so much data for the next decade and really changing the landscape of what we can do in terms of understanding cosmology. So we have the Euclid satellite, which launched a couple of years ago. So that's the bottom. The satellite itself is in the bottom left here, and the image on the right is from Euclid. This is the first one of the first images from Euclid. We also have an equivalent like ground-based project, so a telescope on the ground, which is the Vera Rubin Observatory, same Rubin as I was mentioning before, named after her. And that is showed also on the bottom here, but the image on the top left is from that observatory. And we're seeing these incredibly powerful surveys that are going to hopefully shed just brand new light just from the sheer number of galaxies and the power of the observations. We're going to see like billions of galaxies with these things. So we're going to hopefully be able to really probe our standard cosmological model and not just understand more about dark energy and dark matter, but also like Manos was saying, start to dig really deep into these tensions that we're seeing. So one thing that I'll just mention super quickly is that one of the things we are seeing is that the parameter of our cosmological model, the Hubble constant that describes the expansion of the universe, we have been measuring different values for that from the light from, if we do that measurement using light from the cosmic microwave background or from these kinds of galaxy surveys, lower redshift surveys that see supernova and galaxies. And so this is not what we expect if our model is correct, right? So is this because of something we don't understand about our data, or is this something that is a result of needing to update our model and include some new physics that could be really exciting and revelatory? So I'll stop there because I think I'm at time, but I think we now have time for some questions for both of us.
Okay, so thank you very much for that very interesting presentation. Thank you both again for opening up the conversation so much. So it may be a good time to hear from the student. Iman already had a question from the chat. Is it possible to find where was the point in which the Big Bang happened? Okay, Manos, I think you were referring to that
very
question.
briefly till the next question. I think Pieros also asked it. The issue is the following, that if you take any point of the universe today and you trace it back towards the Big Bang, then all points will concentrate in one space-time point. Actually, the Big Bang, this is how we say, it happened everywhere and nowhere. So all points of the observable universe goes back to the moment of the explosion. So the Big Bang happened everywhere.
If the universe is always expanding for more points, does that mean that the planets and other objects expand as well?
The issue is that the universe at large scales, it expands. Locally, for instance, you can have an asteroid falling on Earth. So the whole universe expands for the moment. However, indeed, in the future, one could ask, what is the fate of the universe? And according to one possibility, the expansion will accelerate forever. So yes, eventually everything will tear apart, even the planets, even the atoms. But for the moment, when we are talking about the expansion of the universe, we mean at large scales, not locally.
Yeah, I would say another way to think about that, I totally agree. Another way to think about that might help is like the other things that you think about as affecting whether things fall together or fall apart still exist. And so on the scales where you're close together, like within an atom or within the solar system, if you think about a system which has really strong forces holding it together, like within the solar system with gravity, or within an atom with the forces within an atom, at the moment those kind of are winning, if that makes sense. But the expansion, like Mano said, will, if it keeps going forever, will eventually start to win over those local forces.
How do we know? I mean, this goes back to what we were saying about how do we know that the same laws hold in different galaxies?
I guess this goes back to what Manos was saying about the cosmological principle. So I think, in fact, we don't know for sure, right? We don't know for sure, but we kind of, the cosmological principle is sort of a statement that we believe that the universe is playing fair with us. And if the laws of physics are actually completely different here versus somewhere else in the universe, in a different galaxy, like that could be true, but we honestly might as well give up at that point. And this is not maybe a very comforting answer. Maybe a better answer is to say that, like, although we don't know for sure, there is evidence that things that are implications of the idea that, like, we do have the cosmological principle have been observed. So we do know that the distribution of galaxies is homogeneous and isotropic on large scales. So there is evidence to suggest that, like, things basically work the same in different places. But it's a fair question. Manos, do you want to jump in and comfort people slightly more than that, perhaps?
No, I totally agree with your answer. It's exactly like that. Probably I could move. There are two related questions. The next one, will there ever be a point where the expansion stops and the universe starts to contract again? And a similar question, is it possible for the expansion to rip a hole in the universe? Well, actually, these questions have to do with the fate, the future of the universe. We are not sure about that. So yes, there is one possibility that the universe expansion will decelerate, and actually it may stop one day, and then we will start the contraction phase, going to what we call a big crunch. So the opposite, the reversed procedure of the Big Bang. This is one possibility. One other possibility is the next question, that if the universe accelerates, if the universe expansion is accelerated forever, then probably, and if it does it in a very fast way, probably we could end to a big rip. So indeed, space-time will expand so fast that it will rip. And of course, there is a third possibility that the universe will expand forever, and then you are going to have what we call the thermal death of the universe. So everything will expand at infinite distances from everything. So it will be a frozen death part. So all these are possibilities on the fate of the universe.
So we have a question from Emma from Louis from Marseille. Emma, what's your question?
Perfect. Go ahead.
How did you get 13.8 billion years? How do we know that's how long ago the Big Bang was?
It's very simple. If you know the rate that the universe expands, you can reverse time and find the rate that the universe was closer and closer and closer. So if you put down the numbers, since we know the Hubble function, so the rate that the universe expands, 1 over this value will be roughly the time, the age of the observable universe. So this is how we found that. We know how fast the universe expands. So going back in time, this will get you to the initial moment of the observable universe. And this is how we find roughly 14 billion years.
There is one in the chat about where do you end up if you travel through a black hole. I think you probably end up pretty dead, but I don't know that we know for sure. Would anybody else like? I mean, okay, so the true answer is like we think that black holes, so black hole, we didn't actually touch on this, I guess. So for those who might not know, like a black hole is a region of space-time where there's such a high concentration of density and mass that the space-time curvature that Manos introduced is so high that even light could not escape. And so that's why it's black, because we can't see light from it because the light goes in and never comes out. And so we think that there are massive black holes in the middle of most galaxies, as well as black holes that are more around the mass of like a star like our sun throughout galaxies. And I think if you just take a sort of practical extension of what we know about gravity, okay, it's a region where you have a very high concentration of density. You go in, you can't come out. I mean, you're probably just kind of sort of dead and in an area where there's a high concentration of density. But from a mathematical perspective, black holes are very interesting objects, and there's all kinds of weird effects that happen theoretically when you go into these really high density regions, analogous to what Manos was talking about with time dilation, time changing when you fly in an airplane. Like things get very wibbly wobbly, timey wimey when you start going into these very high density regions within general relativity. And so the real answer is like we don't know. So one like sort of example of this is that people talk about is that when you go over what's called the event horizon of a black hole, so that's the point at which the light really can no longer come back out, like nothing can ever come back out. When you go through that region, like if you do the calculations as though you are an observer going through that region, you find that like your perception might be that like you never really, things slow down so much that you never get to the middle, and like things like this. Like one funny word that people sometimes throw around to discuss this is spaghettification, because everything gets stretched out. So the answer is we can do some math and try to figure out like some of the weird effects, but we don't know.
There's a question on baby universes and another one on primordial black holes.
As we said, it's an indirect deduction, and our result that our observable universe is not everything, because if inflation has happened, we have huge regions beyond our observable universe. So this is an indirect result, but we are almost sure that this is the case. Now, what will be the laws in these other parts of the universe? We don't know, for instance, whether there will be stars or everything. And but we know that these exist. Be careful that in the literature there is a not so good terminology. Some people are calling these regions parallel universe, but this is not correct in a sense that in another universe, a parallel universe, we are also discussing, but we are wearing other clothes. It's not like that. It's not like that. These are just other regions beyond our observable universe, and that's it.
Okay, so we
Interesting to
have what is
encourage.
the difference between primordial black holes and those from stellar collapse? So primordial black holes are, again, I don't think something we mentioned, but it's basically the idea that you could have black holes from the very early universe that could form some part of the dark matter. So to be honest, I don't know so much about primordial black holes, but I can say a little bit about stellar collapse. So stellar collapse, black holes from stellar collapse occur when you have a very massive star which is going to sort of reach the end of its life cycle as a star where it's burning hydrogen, and it will become a red giant as a result of sort of chemical processes within the star. So it'll get much bigger. It's going to basically burn elements in its core for until it gets to a certain point, and then we're going to have a supernova explosion. And the core of that star is going to end up, if it is massive enough at the beginning, the core of that star is actually going to end up being a black hole just because of the very, very high density in the small area. So that's the origin of stellar mass black holes.
And there are the last burning questions.
I think there is one in the chat. What caused the Big Bang? And actually, welcome to the club of those that were asking this question. The issue is that we don't know. We have the feeling that it was a form of quantum fluctuations of nothing, that something appeared, but we don't know that. So I guess that amongst you are our future colleagues, and all together we're going to answer this question.
So thank you to everyone once again. Thank you to the speakers, to the students, and to the educators, to everyone taking part here. Please follow our network, our action. We have lots of other things going on.